The image shows radish plants of various heights sprouting out of dirt. Figure 5. 1. The heights of these radish plants are continuous random variables. Credit: modification of work, radish, Raphanus sativus. White rust caused by Albugo candida, by Scott Nelson Flicker, public domain. Chapter objectives. By the end of this chapter, the student should be able to recognize and understand continuous probability density functions in general, recognize the uniform probability distribution and apply it appropriately, recognize the exponential probability distribution and apply it appropriately. Continuous random variables have many applications. Baseball batting averages, IQ scores, the length of time a long-distance telephone call lasts, the amount of money a person carries, the length of time a computer chip lasts, and SAT scores are just a few. The field of reliability depends on a variety of continuous random variables. Note: the values of discrete and continuous random variables can be ambiguous. For example, if x is equal to the number of miles to the nearest mile you drive to work, then x is a discrete random variable. You count the miles. If x is the distance you drive to work, then you measure values of x, and x is a continuous random variable. For a second example, if x is equal to the number of books in a backpack, then x is a discrete random variable. If x is the weight of a book, then x is a continuous random variable because weights are measured. How the random variable is defined is very important. Properties of continuous probability distributions. The graph of a continuous probability distribution is a curve. Probability is represented by area under the curve. The curve is called the probability density function, abbreviated as PDF. We use the symbol fx to represent the curve. Fx is the function that corresponds to the graph. We use the density function fx to draw the graph of the probability distribution. Area under the curve is given by a different function called the cumulative distribution function, abbreviated as CDF. The cumulative distribution function is used to evaluate probability as area. The outcomes are measured, not counted. The entire area under the curve and above the x-axis is equal to 1. Probability is found for intervals of x values rather than for individual x values. P, CXD, is the probability that the random variable x is in the interval between the values c and d. P, CXD is the area under the curve, above the x-axis, to the right of c and the left of dp. X equals c equals the probability that x takes on any single individual value is 0. The area below the curve, above the x-axis, and between x equals c and x equals c has no width, and therefore no area, area equals 0. Since the probability is equal to the area, the probability is also 0. P, CXD is the same as P, c less or equal to x less or equal to d, because probability is equal to area. We will find the area that represents probability by using geometry, formulas, technology, or probability tables. In general, calculus is needed to find the area under the curve for many probability density functions. When we use formulas to find the area in this textbook, the formulas were found by using the techniques of integral calculus. However, because most students taking this course have not studied calculus, we will not be using calculus in this textbook. There are many continuous probability distributions. When using a continuous probability distribution to model probability, the distribution used is selected to model and fit the particular situation in the best way. In this chapter and the next, we will study the uniform distribution, the exponential distribution, and the normal distribution. The following graphs illustrate these distributions. This graph shows a uniform distribution. The horizontal axis ranges from 0 to 10. The distribution is modeled by a rectangle extending from x equals 2 to x equals 8. A region from x equals 3 to x equals 6 is shaded inside the rectangle. The shaded area represents P, 3x6. Figure 5. 2. The graph shows a uniform distribution with the area between x equals 3 and x equals 6 shaded to represent the probability that the value of the random variable x is in the interval between 3 and 6. This graph shows an exponential distribution. The graph slopes downward. It begins at a point on the y-axis and approaches the x-axis at the right edge of the graph. The region under the graph from x equals 2 to x equals 4 is shaded to represent px4. Figure 5. 3. The graph shows an exponential distribution with the area between x equals 2 and x equals 4, shaded to represent the probability that the value of the random variable x is in the interval between 2 and 4. This is a normal distribution curve over a horizontal axis labeled from 3 to 3 in intervals of 1. The peak of the curve coincides with the point 0 on the horizontal axis. Vertical lines extend from 1 and 2 to the curve. The area between the lines is shaded. Text note states, shaded area represents probability P, 1x2. Figure 5. 4. The graph shows the standard normal distribution with the area between x equals 1 and x equals 2 shaded to represent the probability that the value of the random variable x is in the interval between 1 and 2. We begin by defining a continuous probability density function. We use the function notation f(x). Intermediate algebra may have been your first formal introduction to functions. In the study of probability, the functions we study are special. We define the function f(x) so that the area between it and the x-axis is equal to a probability. Since the maximum probability is 1, the maximum area is also 1. For continuous probability distributions, probability equals area. Example 5. 1. Consider the function f(x) equals 120. For 0 less or equal to x less or equal to 20, x equals a real number. The graph of f(x) equals 120 is a horizontal line. However, since 0 less or equal to x less or equal to 20, f(x) is restricted to the portion between x equals 0 and x equals 20, inclusive. This shows the graph of the function f(x) equals 120. A horizontal line ranges from the point 0, 120 to the point 20, 120. A vertical line extends from the x-axis to the end of the line at point 20, 120, creating a rectangle. Figure 5.5. f(x) equals 120. For 0 less or equal to x less or equal to 20. The graph of f(x) equals 120 is a horizontal line segment when 0 less or equal to x less or equal to 20. The area between f(x) equals 120, where 0 less or equal to x less or equal to 20, and the x-axis is the area of a rectangle with base equals 20 and height equals 120. Area equals 20, 120 equals 1. Suppose we want to find the area between f(x) equals 120 and the x-axis where x2. This shows the graph of the function f(x) equals 120. A horizontal line ranges from the point 0, 120 to the point 20, 120. A vertical line extends from the x-axis to the end of the line at point 20, 120, creating a rectangle. A region is shaded inside the rectangle from x equals 0 to x equals 2. Figure 5. 6. Area equals 2, 0. 120 equals 0, 1. 2, 0 equals 2 equals base of a rectangle. Reminder: area of a rectangle equals base, height. The area corresponds to a probability. The probability that x is between 0 and 2 is 0, 1. Which can be written mathematically as P0x2 equals P x2 equals 0, 1. Suppose we want to find the area between f(x) equals 120 and the x-axis where 4x15. This shows the graph of the function f(x) equals 120. A horizontal line ranges from the point 0, 120 to the point 20, 120. A vertical line extends from the x-axis to the end of the line at point 20, 120, creating a rectangle. A region is shaded inside the rectangle from x equals 4 to x equals 15. Figure 5-7. Area equals 15, 4. 120 equals 0. 55. 15, 4 equals 11 equals the base of a rectangle. The area corresponds to the probability P, 4x 15 equals 0.55. Suppose we want to find P, x equals 15. On an xy graph, x equals 15 is a vertical line. A vertical line has no width or zero width. Therefore, P, x equals 15 equals base, height equals 0, 120, equals 0. This shows the graph of the function f(x) equals 120. A horizontal line ranges from the point 0, 120 to the point 20, 120. A vertical line extends from the x-axis to the end of the line at point 20, 120, creating a rectangle. A vertical line extends from the horizontal axis to the graph at x equals 15. Figure 5-8. P, x less or equal to x, which can also be written as P, xx, for continuous distributions, is called the cumulative distribution function or CDF. Notice the less than or equal to symbol. We can also use the CDF to calculate P, xx. The CDF gives area to the left and P, xx, gives area to the right. We calculate P, xx for continuous distributions as follows. P, xx equals 1 P, xx. This shows the graph of the function f(x) equals 120. A horizontal line ranges from the point 0, 120 to the point 20, 120. A vertical line extends from the x-axis to the end of the line at point 20, 120, creating a rectangle. The area to the left of a value x is shaded. Figure 5-9. Label the graph with f, x, and x scale the x and y axes with the maximum x and y values. Fx equals 120. 0 less or equal to x less or equal to 20. To calculate the probability that x is between two values, look at the following graph. Shade the region between x equals 2, 3 and x equals 12, 7. Then calculate the shaded area of a rectangle. This shows the graph of the function f(x) equals 120. A horizontal line ranges from the point 0, 120 to the point 20, 120. A vertical line extends from the x-axis to the end of the line at point 20, 120, creating a rectangle. A region is shaded inside the rectangle from x equals 2, 3 to x equals 12, 7. Figure 5. 10. Letter 1 D4432. 3 letter 1 D465 12. 7 equals base, height equals 12, 7 minus 2, 3, 120 equals 0, 52. Try it 5. 1. Consider the function f(x) equals 18. For 0 less or equal to x less or equal to 8, draw the graph of f(x) and find P2, 5x75. The uniform distribution is a continuous probability distribution and is concerned with events that are equally likely to occur. When working out problems that have a uniform distribution, be careful to note if the data is inclusive or exclusive of endpoints. Example 5. 2. The data in Table 5.1 are 55 smiling times in seconds of an 8-week-old baby. 10, 4:19, 6:18, 8:13, 9:17, 8:16, 8:21, 6:17, 9:12, 5:11, 1:4, 9:12, 8:14, 8:22, 8:20, 0:15, 9:16, 3:13, 4:17, 1:14, 5:19, 0:22, 8:130, 7:8, 9:11, 9:10, 9:735, 9:3717, 9:19, 29, 8:5, 8:6, 9:265, 8:21, 7:11, 8:342, 1:456, 3:10, 7:8, 9:949, 4:7610, 0.33677811, 6.13, 8.18, 6 Table 5. 1. The sample mean equals 11.65 and the sample standard deviation equals 6.8. We will assume that the smiling times in seconds follow a uniform distribution between 0 and 23 seconds, inclusive. This means that any smiling time from 0 to and including 23 seconds is equally likely. The histogram that could be constructed from the sample is an empirical distribution that closely matches the theoretical uniform distribution. Let x equals length in seconds of an 8-week-old baby's smile. The notation for the uniform distribution is xu, a, b, where a equals the lowest value of x and b equals the highest value of x. The probability density function is f, x, equals 1 letter 1d44f minus letter 1d44e for a less or equal to x less or equal to b. For this example, xu, 0, 23, and f, x, equals 123 minus 0 for 0 less or equal to x less or equal to 23. Formulas for the theoretical mean and standard deviation are letter 1d707 equals letter 1d44e plus letter 1d44f2 and letter 1d70e equals letter 1d44f minus letter 1d44e. 212 square for this problem. The theoretical mean and standard deviation are mu equals 0 plus 232 equals 11. 50 seconds and sigma equals 23 minus 0, 212 square equals 664 seconds. Notice that the theoretical mean and standard deviation are close to the sample mean and standard deviation in this example. Try it 5. 2. The data that follow record the total weight to the nearest pound of fish caught by passengers on 35 different charter fishing boats on one summer day. The sample mean equals 7.9 and the sample standard deviation equals 433. The data follow a uniform distribution where all values between and including 0 and 14 are equally likely. State the values of A and B. Write the distribution in proper notation, and calculate the theoretical mean and standard deviation. 1, 12, 4, 10, 4, 14, 11, 7, 11, 4, 13, 2, 4, 6, 3, 10, 0, 12, 6, 9, 10, 5, 13, 4, 10, 14, 12, 11, 6, 10, 11, 0, 11, 13, 2, Table 5. 2. Example 5.3 Problem A. Refer to Example 5.2. What is the probability that a randomly chosen 8-week-old baby smiles between 2 and 18 seconds? Solution P. 2 x 18 equals base. Height equals 18 2. 123 equals 1623. This graph shows a uniform distribution. The horizontal axis ranges from 0 to 15. The distribution is modeled by a rectangle extending from x equals 0 to x equals 15. A region from x equals 2 to x equals 18 is shaded inside the rectangle. Figure 5.11 Problem B. Find the 90th percentile for an 8-week-old baby's smiling time. Solution B. 90% of the smiling times fall below the 90th percentile. K, so P, xk equals 0. 90, letter 1d443, letter 1d465, letter 1d458 equals 0. 90 base, height equals 0. 90, letter 1d458 minus 0. 123 equals 0. 90, letter 1d458 equals 23, 0. 90 equals 20. 7. This shows the graph of the function f(x) equals 115. A horizontal line ranges from the point 0, 115 to the point 15, 115. A vertical line extends from the x-axis to the end of the line at point 15, 115, creating a rectangle. A region is shaded inside the rectangle from x equals 0 to x equals k. The shaded area represents P, xk, equals 0, 90. Figure 5.12 Problem C. Find the probability that a random 8-week-old baby smiles more than 12 seconds knowing that the baby smiles more than 8 seconds. Solution C. This probability question is a conditional. You are asked to find the probability that an 8-week-old baby smiles more than 12 seconds when you already know the baby has smiled for more than 8 seconds. Find p x 12 x 8. There are two ways to do the problem. For the first way, use the fact that this is a conditional and changes the sample space. The graph illustrates the new sample space. You already know the baby smiled more than 8 seconds. Write a new fx. Fx equals 123 minus 8 equals 115 for 8x23p. x12x 8 equals 23 minus 12. 115 equals 1115f. X equals 1/15 graph displaying a boxed region consisting of a horizontal line extending to the right from point 115 on the y-axis, a vertical upward line from points 8 and 23 on the x-axis, and the x-axis. A shaded region from points 12-23 occurs within this area. Figure 5.13 for the second way. Use the conditional formula from probability topics with the original distribution xu 0, 23. P a b equals letter 1 d443, letter 1 d434 and letter 1 d435, letter 1 d443, letter 1 d435. For this problem, A is x12 and B is x8. So, P x12 x8 equals letter 1 d443. Letter 1 d465 12 and letter 1 d465 8, letter 1 d443. Letter 1 d465 8 equals letter 1 d443. Letter 1 d465 12, letter 1 d443. Letter 1 d465 8 equals 11,230,1523 equals 1,115. This diagram shows a horizontal x-axis that intersects a vertical f of x-axis at the origin. The x-axis runs from 0 to 24, while the y-axis only has the fraction 1/23 located about 2/3 of the way to the top. A rectangular box extends horizontally from 0 to 23 on the x-axis. The box extends vertically up to the fraction 1/23 on the f of x-axis. The area of the box between 8 and 12 on the x-axis is lightly shaded. The area of the box between 12 and 23 has darker shading. Figure 5. 14 darker shaded area represents p x 12. Entire shaded area shows p x 8. Try at 5. 3. A distribution is given as xu 0, 20. What is p 2 x 18? Find the 90th percentile. Example 5. For the amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes, inclusive. Problem A. What is the probability that a person waits fewer than 5 minutes? B. On the average, how long must a person wait? Find the mean, mu, and the standard deviation, sigma. C. 90% of the time a person must wait falls below what value? This asks for the 90th percentile. Solution A. Let x equals the number of minutes a person must wait for a bus. A equals 0 and B equals 15. xu 0, 15. Write the probability density function. Fx equals 115 minus 0 equals 115 for 0 less or equal to x less or equal to 15. Find p x 12 5. Draw a graph. Letter 1 d443, letter 1 d465, letter 1 d458 equals base, height equals 12, 5 minus 0, 115 equals 0. 8333. The probability a person waits less than 5 minutes is 0. 8333. This shows the graph of the function f, x equals 115. A horizontal line ranges from the point 0, 115 to the point 15, 115. A vertical line extends from the x-axis to the end of the line at point 15, 115, creating a rectangle. A region is shaded inside the rectangle from x equals 0 to x equals 12. 5 Figure 5 15 B mu equals A plus B2 equals 15 plus 2 equals 7. 5. On the average, a person must wait 5 minutes. Sigma equals letter 1d4 4f minus letter 1d4 4e, 212 square equals 15 minus 0, 212 square equals 4. 3. The standard deviation is 3 minutes. C. Find the 90th percentile. Draw a graph. Let k equals the 90th percentile. Letter 1d443, letter 1d465, letter 1d458 equals base. Height equals letter 1d458 minus 0, 115, 0. 90 equals letter 1d458, 115, letter 1d458 equals 0. 90, 15 equals 13. 5k is sometimes called a critical value. The 90th percentile is 13. 5 minutes. 90% of the time, a person must wait at most 5 minutes. Fx equals 1/15 graph displaying a boxed region consisting of a horizontal line extending to the right from point 115 on the y-axis, a vertical upward line from an arbitrary point on the x-axis, and the x and y-axes. A shaded region from point 0k occurs within this area. The area of this probability region is equal to 0.90. Figure 5. 16. Try it 5. 4. The total duration of baseball games in the Major League in a typical season is uniformly distributed between 447 hours and 521 hours inclusive. Find A and B and describe what they represent. Write the distribution. Find the mean and the standard deviation. What is the probability that the duration of games for a team for a single season is between 480 and 500 hours? What is the 65th percentile for the duration of games for a team in a single season? Example 5. 5. Suppose the time it takes a 9-year-old to eat a donut is between 0.5 and 4 minutes, inclusive. Let x equals the time in minutes it takes a 9-year-old child to eat a donut. Then xu, 0.5, 4. Problem A. The probability that a randomly selected 9-year-old child eats a donut in at least 2 minutes is. B. Find the probability that a different 9-year-old child eats a donut in more than 2 minutes, given that the child has already been eating the donut for more than 5 minutes. The second question has a conditional probability. You are asked to find the probability that a 9-year-old child eats a donut in more than 2 minutes given that the child has already been eating the donut for more than 5 minutes. Solve the problem 2 different ways. See example 5.3. You must reduce the sample space. First way. Since you know the child has already been eating the donut for more than 5 minutes, you are no longer starting at a equals 0.5 minutes. Your starting point is 5 minutes. Write a new fx. Fx equals 14 minus 1. 5 equals 25 for 5 less or equal to x less or equal to 4. Find p, x2, x15. Draw a graph. Fx. Graph displaying a boxed region consisting of a horizontal line extending to the right from point 25 on the y-axis, a vertical upward line from points 5 and 4 on the x-axis and the x-axis. A shaded region from points 2-4 occurs within this area. Figure 5.17p, x2, x15 equals base. New height equals 4 minus 2, 25 equals 45. Solution A. 0. 5714 B 45. The probability that a 9-year-old child eats a donut in more than 2 minutes given that the child has already been eating the donut for more than 5 minutes is 45. Second way. Draw the original graph for xu 054. Use the conditional formula p, x2, x15 equals letter 1d443. Letter 1d4652 and letter 1d4651. 5 letter 1d443, letter 1d4651. 5 equals letter 1d443, letter 1d4652, letter 1d443, letter 1d4651. 5 equals 23. 52, 53. 5 equals 0. 8 equals 45. Try it. 5. 5. Suppose the time it takes a student to finish a quiz is uniformly distributed between 6 and 15 minutes, inclusive. Let x equals the time in minutes it takes a student to finish a quiz. Then xu 6, 15. Find the probability that a randomly selected student needs at least 8 minutes to complete the quiz. Then find the probability that a different student needs at least 8 minutes to finish the quiz given that she has already taken more than 7 minutes. Example 5. 6. Ace Heating and Air Conditioning Service finds that the amount of time a repair tech needs to fix a furnace is uniformly distributed between 1-5 and 4 hours. Let x equals the time needed to fix a furnace. Then xu 1-5, 4. Problem: find the probability that a randomly selected furnace repair requires more than 2 hours. Find the probability that a randomly selected furnace repair requires less than 3 hours. Find the 30th percentile of furnace repair times. The longest 25% of furnace repair times take at least how long? In other words, find the minimum time for the longest 25% of repair times. What percentile does this represent? Find the mean and standard deviation solution A to find fx. Fx equals 14 minus 15 equals 12. 5, so fx equals 0. 4px2 equals base. Height equals 420. 4 equals 0. 8. This shows the graph of the function fx equals 0, 4. A horizontal line ranges from the point 150, 4 to the point 4, 0, 4. Vertical lines extend from the x-axis to the graph at x equals 15 and x equals 4, creating a rectangle. A region is shaded inside the rectangle from x equals 2 to x equals 4. Figure 5. 18. Uniform distribution between 1-5 and 4 with shaded area between 2 and 4, representing the probability that the repair time x is greater than 2b. Px3 equals base. Height equals 315, 0. 4 equals 0. 6. The graph of the rectangle showing the entire distribution would remain the same. However, the graph should be shaded between x equals 1, 5 and x equals 3. Note that the shaded area starts at x equals 15 rather than at x equals 0. Since xu 15, 4, x cannot be less than 15. This shows the graph of the function fx equals 0, 4. A horizontal line ranges from the point 15, 0, 4 to the point 4, 0, 4. Vertical lines extend from the x-axis to the graph at x equals 15 and x equals 4, creating a rectangle. A region is shaded inside the rectangle from x equals 15 to x equals 3. Figure 5. 19. Uniform distribution between 1-5 and 4 with shaded area between 1-5 and 3, representing the probability that the repair time x is less than 3c. This shows the graph of the function fx equals 0, 4. A horizontal line ranges from the point 15, 0, 4 to the point 4, 0, 4. Vertical lines extend from the x-axis to the graph at x equals 15 and x equals 4, creating a rectangle. A region is shaded inside the rectangle from x equals 15 to x equals k. The shaded area represents p, xk, equals 0, 3. Figure 5. 20. Uniform distribution between 1-5 and 4 with an area of 0. 30 shaded to the left, representing the shortest 30% of repair times. Pxk equals 0, 30. Pxk equals base. Height equals k1, 5, 0. 4, 0, 3 equals k1, 5, 0, 4. Solve to find k. 0, 75 equals k1. 5. Obtained by dividing both sides by 0. 4k equals 225. Obtained by adding 15 to both sides. The 30th percentile of repair times is 225 hours. 30% of repair times are 225 hours or less. D. This shows the graph of the function fx equals 0, 4, the PDF for a uniform distribution. A horizontal line ranges from the point 1,504 to the point 404. Vertical lines extend from the x-axis to the graph at x equals 15 and x equals 4, creating a rectangle. A region is shaded inside the rectangle from x equals k for 15k4 to x equals 4. Text notes that the shaded area represents p, xk equals 0.25. Figure 5. 21 uniform distribution between 15 and 4 with an area of 0. 25 shaded to the right representing the longest 25% of repair times. P, xk equals 0. 25p xk equals base, height equals 4k 0. 4025 equals 4k 0. 4. Solve for k 0. 625 equals 4 minus k, obtained by dividing both sides by 0. 4 minus 3. 375 equals minus k, obtained by subtracting 4 from both sides. K equals 3. 375. The longest 25% of furnace repairs take at least 375 hours. 375 hours or longer. Note: since 25% of repair times are 375 hours or longer, that means that 75% of repair times are 375 hours or less. 3. 375 hours is the 75th percentile of furnace repair times. Letter 1D707 equals letter 1D44E plus letter 1D44F2 and letter 1D70E equals letter 1D44F minus letter 1D44E. 212 square letter 1D707 equals 1. 5 plus 42 equals 2. 75 hours and letter 1D70E equals 4 1. 5 at 212 square equals 0. 7217 hours. Try it. 5. 6. The amount of time a service technician needs to change the oil in a car is uniformly distributed between 11 and 21 minutes. Let x equals the time needed to change the oil on a car. Write the random variable x in words. X equals, write the distribution, graph the distribution, find p x 19, find the 50th percentile. The exponential distribution is often concerned with the amount of time until some specific event occurs. For example, the amount of time, beginning now, until an earthquake occurs has an exponential distribution. Other examples include the length, in minutes, of long-distance business telephone calls, and the amount of time, in months, a car battery lasts. It can be shown, too, that the value of the change that you have in your pocket or purse approximately follows an exponential distribution. Values for an exponential random variable occur in the following way. There are fewer large values and more small values. For example, the amount of money customers spend in one trip to the supermarket follows an exponential distribution. There are more people who spend small amounts of money and fewer people who spend large amounts of money. Exponential distributions are commonly used in calculations of product reliability, or the length of time a product lasts. Example 5.7. Let x equals amount of time, in minutes, a postal clerk spends with their customer. The time is known to have an exponential distribution with the average amount of time equal to 4 minutes. X is a continuous random variable since time is measured. It is given that mu equals 4 minutes. To do any calculations, you must know m, the decay parameter. Letter 1D45A equals 1 letter 1D707. Therefore, letter 1D45A equals 14 equals 0. 25. The standard deviation, sigma, is the same as the mean. Mu equals sigma. The distribution notation is x exp m. Therefore, x exp 0. 25. The probability density function is fx equals me mx. The number e equals 2. 71,828,180,2,846. It is a number that is used often in mathematics. Scientific calculators have the key x. If you enter 1 for x, the calculator will display the value the curve is f(x) equals 0, 25e0, 25x where x is at least 0 and m equals 0, 25. For example, f5 equals 25e minus 0, 25, 5 equals 0, 72. The value 0, 72 is the height of the curve when x equals 5, in example 5. 8 below, you will learn how to find probabilities using the decay parameter. The graph is as follows. Exponential graph with increments of 2 from 0 to 20 on the x-axis of mu equals 4 and increments of 0. 5 from 0. 5, 0, 25 on the y-axis of m equals 0, 25. The curved line begins at the top at point 0, 0, 25 and curves down to point 20, 0. The x-axis is equal to a continuous random variable. Figure 5. 22. Notice the graph is a declining curve. When x equals 0, fx equals 0. 25e minus 0. 25, 0 equals 0, 25. 1 equals 0, 25 equals m. The maximum value on the y-axis is m. Try it 5. 7. The amount of time spouses shop for anniversary cards can be modeled by an exponential distribution with the average amount of time equal to 8 minutes. Write the distribution, state the probability density function, and graph the distribution. Example 5.8 Problem A using the information in example 5. 7. Find the probability that a clerk spends 4 to 5 minutes with a randomly selected customer. Solution A. Find P, 4x5. The cumulative distribution function, CDF, gives the area to the left. Pxx equals 1e, mxpx5 equals 1e minus 0, 25, 5 equals 0, 71, 35 and px4 equals 1e 0, 25, 4 equals 0. 63, 21 Exponential graph with the curved line beginning at point 0, 0, 25 and curves down towards point infinity, 0. 2 vertical upward lines extend from points 4 and 5 to the curved line. The probability is in the area between points 4 and 5. Figure 5.23 Note you can do these calculations easily on a calculator. The probability that a postal clerk spends 4 to 5 minutes with a randomly selected customer is P4x5 equals Px5. Px4 equals 0. 7135 minus 0, 6321 equals 0, 814. Using the T83, 83 plus 84, 84 plus calculator on the home screen, enter 1, E, 0. 25 asterisk 5, 1, E, 0. 25 asterisk 4 or enter E, 0. 25 asterisk 4, E, 0. 25 asterisk 5. Problem B. Half of all customers are finished within how long? Find the 50th percentile. Solution B. Find the 50th percentile. Exponential graph with the curved line beginning at point 0, 0, 25 and curves down towards point infinity, 0. A vertical upward line extends from point K to the curved line. The probability area from 0K is equal to 0, 50. Figure 5.24 P x K equals 0, 50, K equals 2. 8 minutes calculator or computer. Half of all customers are finished within 8 minutes. You can also do the calculation as follows. P x K equals 0, 50 and P x K equals 1, E 0. 25K therefore 0. 50 equals 1 minus E minus 0. 25K and E minus 0. 25K equals 1 minus 0. 50 equals 0, 5 take natural logs, ln E 0. 25K equals ln 0, 50. So 0, 25K equals ln 0, 50. Solve for K. Letter 1 D458 equals letter 1 D459 letter 1 D45B 0. 50 minus 0. 25 equals 2. 8 minutes. The calculator simplifies the calculation for percentile K. See the following 2 notes. Note a formula for the percentile K. is letter 1D458 equals letter 1D459, letter 1D45B. 1 minus letter 1D434, letter 1D45F, letter 1D452, letter 1D440, letter 1D447, letter 1D45C, letter 1D447, letter 210E, letter 1D452, letter 1D43F, letter 1D452, letter 1D453, letter 1D461 minus letter 1D45A, where ln is the natural log. Using the T83, 83 plus 84, 84 plus calculator on the home screen, enter ln 10, 50/0, 25. Press the for the negative, problem C. Which is larger, the mean or the median? Solution C from part B, the median or 50th percentile is 28 minutes. The theoretical mean is 4 minutes. The mean is larger, try at 5. 8. The number of days ahead travelers purchase their airline tickets can be modeled by an exponential distribution, with the average amount of time equal to 15 days. Find the probability that a traveler will purchase a ticket fewer than 10 days in advance. How many days do half of all travelers wait? Collaborative exercise: have each class member count the change they have in their pocket or purse. Your instructor will record the amounts in dollars and cents. Construct a histogram of the data taken by the class. Use 5 intervals. Draw a smooth curve through the bars. The graph should look approximately exponential. Then calculate the mean. Let x equals the amount of money a student in your class has in their pocket or purse. The distribution for x is approximately exponential with mean, mu equals and m equals. The standard deviation, sigma, equals. Draw the appropriate exponential graph. You should label the x and y axes, the decay rate, and the mean. Shade the area that represents the probability that one student has less than 40 in their pocket or purse. Shade P x 040, example 5. 9. On the average, a certain computer part lasts 10 years. The length of time the computer part lasts is exponentially distributed. Problem A. What is the probability that a computer part lasts more than 7 years? Solution A. Let x equals the amount of time, in years, a computer part lasts. Mu equals 10, so letter 1D45A equals 1, letter 1D707 equals 110 equals 0. 1. Find P x 7. Draw the graph. P x 7 equals 1 P x 7. Since P x x equals 1 E mx, then P x x equals 1 E mx equals EMX. P x 7 equals E0. 1, 7 equals 0. 4966. The probability that a computer part lasts more than 7 years is 0. 4966. Using the T83, 83 plus 84, 84 plus calculator on the home screen, enter E. 1*7. Exponential graph with the curved line beginning at point 0, 0, 1 and curves down towards point infinity, 0. A vertical upward line extends from point 1 to the curved line. The probability area occurs from point 1 to the end of the curve. The x-axis is equal to the amount of time a computer part lasts. Figure 5.25, problem B. On the average, how long would 5 computer parts last if they are used one after another? Solution B. On the average, one computer part lasts 10 years. Therefore, 5 computer parts, if they are used one right after the other, would last, on the average, 5. 10 equals 50 years. Problem C. 80% of computer parts last at most how long? Solution C. Find the 80th percentile. Draw the graph. Let K equals the 80th percentile. Exponential graph with the curved line beginning at point 0, 0, 1 and curves down towards point infinity, 0. A vertical upward line extends from point K to the curved line. K is the 80th percentile. The probability area from 0K is equal to 0.80. Figure 5. 26. Solve for K. Letter 1D458 equals letter 1D459, letter 1D45B, 10, 80, 0. 1 equals 16. 1 year's 80% of the computer parts last at most 16. 1 years. Using the T83, 83 plus 84, 84 plus calculator on the home screen, enter ln 10, 80. 1 Problem D. What is the probability that a computer part lasts between 9 and 11 years? Solution D. Find P, 9x 11. Draw the graph. Exponential graph with the curved line beginning at point 0, 0, 1, and curves down towards point infinity, 0. 2 vertical upward lines extend from point 9 and 11 to the curved line. The probability area occurs between point 9 and 11. Figure 5. 27p9x11 px11 px9 equals 1e0, 1, 11, 1e0, 1, 9 equals 0, 66, 71, 0, 59, 34 equals 0, 737. The probability that a computer part lasts between 9 and 11 years is 0. 737. Using the T83, 83 plus 84, 84 plus calculator on the home screen, enter E0. 1 asterisk 9, E0, 1 asterisk 11, try it 5. 9 on average. A pair of running shoes can last 18 months if used every day. The length of time running shoes last is exponentially distributed. What is the probability that a pair of running shoes last more than 15 months? On average, how long would 6 pairs of running shoes last if they are used one after the other? 80% of running shoes last at most. How long if used every day? Example 5. 10. Suppose that the length of a phone call in minutes is an exponential random variable with decay parameter 112. If another person arrives at a public telephone just before you, find the probability that you will have to wait more than 5 minutes. Let x equals the length of a phone call in minutes. Problem: what is m, mu, and the probability that you must wait more than 5 minutes is? Solution: m equals 112, mu equals 12, sigma equals 12p, x 5 equals 0. 6592, try it 5. 10. Suppose that the distance in miles that people are willing to commute to work is an exponential random variable with a decay parameter 120. Let x equals the distance people are willing to commute in miles. What is m, mu, and sigma? What is the probability that a person is willing to commute more than 25 miles? Example 5. 11. The time spent waiting between events is often modeled using the exponential distribution. For example, suppose that an average of 30 customers per hour arrive at a store, and the time between arrivals is exponentially distributed. Problem: on average, how many minutes elapse between 2 successive arrivals? When the store first opens, how long on average does it take for 3 customers to arrive? After a customer arrives, find the probability that it takes less than 1 minute for the next customer to arrive. After a customer arrives, find the probability that it takes more than 5 minutes for the next customer to arrive. 70% of the customers arrive within how many minutes of the previous customer? Is an exponential distribution reasonable for this situation? Solution: since we expect 30 customers to arrive per hour, 60 minutes, we expect on average 1 customer to arrive every 2 minutes on average. Since 1 customer arrives every 2 minutes on average, it will take 6 minutes on average for 3 customers to arrive. Let x equals the time between arrivals in minutes. By part a, mu equals 2, so m equals 12 equals 0, 5. Therefore x 0, 5. The cumulative distribution function is p x equals 1 e minus 0, 5, x. Therefore p x1 equals 1 e 0, 5, 1 approximately 0, 39, 35. Using the T83, 83 plus 84, 84 plus calculator 1 e 0, 5 approximately 0, 39, 35 exponential graph with the graph beginning at point 0, 0, 5 and curving down towards the horizontal axis, which is an asymptote. A vertical line segment extends from the horizontal axis to the curve at x equals 1. The area under the curve between the y-axis and this segment is shaded. Text states shaded area represents probability 0. 3935. Figure 5. 28p x 5 equals 1p x 5 equals 1 e minus 0, 50, 5 equals e2, 5 approximately 0, 821. Exponential graph with the graph beginning at point 0, 0, 5, and curving down towards the horizontal axis, which is an asymptote. A vertical line segment extends from the horizontal axis to the curve at x equals 5. The area under the curve to the right of this segment is shaded. Text states shaded area represents probability p x 5 equals 1 p x 5 equals 0, 821. Figure 5. 29 using the T83, 83 plus 84, 84 plus calculator 1 e minus 0, 50, 5, or e, 5 asterisk 0, 5, we want to solve 0. 70 equals p xx for x substituting in the cumulative distribution function gives 0. 70 equals 1 e0, 5x so that e0, 5x equals 0, 30. Converting this to logarithmic form gives 0. 5x equals ln 0. 30, or letter 1d465 equals letter 1d459 letter 1d45b, 0. 30, 0. 5 approximately 2. 41 minutes. Thus, 70% of customers arrive within 41 minutes of the previous customer. You are finding the 70th percentile K, so you can use the formula K equals letter 1d459 letter 1d45b. 1 letter 1d434 letter 1d45f letter 1d452 letter 1d44e letter 1d447 letter 1d45c letter 1d447 letter 2 and 0e letter 1d452 letter 1d43f letter 1d452 letter 1d453 letter 1d461 letter 1d442 letter 1d453 letter 1d458 letter 1d45a K equals letter 1d459 letter 1d45b 10 70 0 5 approximately 41 minutes exponential graph with the graph beginning at point 0, 0, 5 and curving down towards the horizontal axis, which is an asymptote. A vertical line segment extends from the horizontal axis to the curve at x equals 241. The area under the curve between the y-axis and this segment is shaded. Text states shaded area represents probability 0. 70. Figure 5. 30. This model assumes that a single customer arrives at a time, which may not be reasonable since people might shop in groups, leading to several customers arriving at the same time. It also assumes that the flow of customers does not change throughout the day, which is not valid if some times of the day are busier than others. Try it 5. 11. Suppose that on a certain stretch of highway, cars pass at an average rate of 5 cars per minute. Assume that the duration of time between successive cars follows the exponential distribution. On average, how many seconds elapse between 2 successive cars? After a car passes by, how long on average will it take for another 7 cars to pass by? Find the probability that after a car passes by, the next car will pass within the next 20 seconds. Find the probability that after a car passes by, the next car will not pass for at least another 15 seconds. Memorylessness of the exponential distribution. In example 5.7, recall that the amount of time between customers is exponentially distributed with a mean of 2 minutes, x exp. 0.5. Suppose that 5 minutes have elapsed since the last customer arrived. Since an unusually long amount of time has now elapsed, it would seem to be more likely for a customer to arrive within the next minute. With the exponential distribution, this is not the case. The additional time spent waiting for the next customer does not depend on how much time has already elapsed since the last customer. This is referred to as the memoryless property. Specifically, the memoryless property says that p xr plus t xr equals p xt for all r greater or equal to 0 and t greater or equal to 0. For example, if 5 minutes have elapsed since the last customer arrived, Then the probability that more than 1 minute will elapse before the next customer arrives is computed by using r equals 5 and t equals 1 in the foregoing equation. P x5 plus 1 x5 equals P x1 equals letter 1 d452 0 5 1 approximately 0 60 65. This is the same probability as that of waiting more than 1 minute for a customer to arrive after the previous arrival. The exponential distribution is often used to model the longevity of an electrical or mechanical device. In example 5.9, the lifetime of a certain computer part has the exponential distribution with a mean of 10 years, x 0. 1. The memoryless property says that knowledge of what has occurred in the past has no effect on future probabilities. In this case, it means that an old part is not any more likely to break down at any particular time than a brand new part. In other words, the part stays as good as new until it suddenly breaks. For example, if the part has already lasted 10 years, then the probability that it lasts another 7 years is P x17 x10 equals P x7 equals 0. 4966. Example 5.12 refer to example 5.7, where the time a postal clerk spends with a customer has an exponential distribution with a mean of 4 minutes. Suppose a customer has spent 4 minutes with a postal clerk. What is the probability that the customer will spend at least an additional 3 minutes with the postal clerk? The decay parameter of x is m equals 14 equals 0. 25, so x 0, 25. The cumulative distribution function is p x equals 1 e0, 25x. We want to find p x7 x4. The memoryless property says that p x7 x4 equals p x3. So we just need to find the probability that a customer spends more than 3 minutes with a postal clerk. This is p x3 equals 1 p x3 equals 1 1 e0. 25 3 equals e0. 75 approximately 0. 47 24. This graph shows an exponential distribution. The graph slopes downward. It begins at the point 0, 0, 25 on the y-axis and approaches the x-axis at the right edge of the graph. The region under the graph to the right of x equals 3 is shaded to represent p x3 equals 0. 47 24, figure 5. 31 using the T83, 83 plus 84, 84 plus calculator 1, 1, E0. 25 asterisk 3 equals E0. 25 asterisk 3. Try it 5. 12. Suppose that the longevity of a light bulb is exponential with a mean lifetime of 8 years. If a bulb has already lasted 12 years, find the probability that it will last a total of over 19 years. Relationship between the Poisson and the exponential distribution. There is an interesting relationship between the exponential distribution and the Poisson distribution. Suppose that the time that elapses between two successive events follows the exponential distribution with a mean of mu units of time. Also assume that these times are independent, meaning that the time between events is not affected by the times between previous events. If these assumptions hold, then the number of events per unit time follows a Poisson distribution with mean lambda equals 1/mu. Recall from the chapter on discrete random variables that if x has the Poisson distribution with mean lambda, then letter 1 d443, letter 1 d44b equals letter 1 d458 equals letter 1 d706, letter 1 d458, letter 1 d452, minus letter 1 d706, letter 1 d458. Conversely, if the number of events per unit time follows a Poisson distribution, then the amount of time between events follows the exponential distribution. K equals K asterisk, K1 asterisk, K2 asterisk, K3 asterisk, 3 asterisk 2 asterisk 1. Using the T83, 83 plus 84, 84 plus calculator, suppose x has the Poisson distribution with mean lambda. Compute p x equals k by entering second vars dister c Poisson lambda k. To compute px less or equal to k, enter second vars distr d Poisson lambda k. Example 5. 13 at a police station in a large city. Calls come in at an average rate of 4 calls per minute. Assume that the time that elapses from one call to the next has the exponential distribution. Take note that we are concerned only with the rate at which calls come in, and we are ignoring the time spent on the phone. We must also assume that the time spent between calls are independent. This means that a particularly long delay between two calls does not mean that there will be a shorter waiting period for the next call. We may then deduce that the total number of calls received during a time period has the Poisson distribution. Problem: find the average time between two successive calls. Find the probability that after a call is received, the next call occurs in less than 10 seconds. Find the probability that exactly 5 calls occur within a minute. Find the probability that less than 5 calls occur within a minute. Find the probability that more than 40 calls occur in an 8-minute period. Solution: on average, there are 4 calls occur per minute, so 15 seconds, or 1560 equals 0. 25 minutes occur between successive calls on average. Let t equals time elapse between calls. From part A, mu equals 0.25, so m equals 10. 25 equals 4. Thus, t x before. The cumulative distribution function is ptt equals 1 e4t. The probability that the next call occurs in less than 10 seconds equals 1/6 minute, is letter 1d443. Letter 1d447 16 equals 1 letter 1d4524. 16, approximately 0. 4866. This graph shows an exponential distribution. The graph slopes downward. It begins at the point 0, 0, 8 on the y-axis and approaches the x-axis at the right edge of the graph. The region under the graph to the left of x equals 20 is shaded to represent p, x16, equals 0.4866. Figure 532, let x equals the number of calls per minute. As previously stated, the number of calls per minute has a Poisson distribution, with a mean of 4 calls per minute. Therefore, x Poisson 4, and so p, x equals 5, equals 45 letter 1d452 minus 45. Approximately 0 1563. 5 equals 5 4 3 2 1. Using the T83, 83 plus 84, 84 plus calculator Poisson, 4 5 equals 0. 1563. Keep in mind that x must be a whole number, so p x5 equals p x less or equal to 4. To compute this, we could take p x equals 0 plus p x equals 1 plus p x equals 2 plus p x equals 3 plus p x equals 4. Using technology, we see that p x less or equal to 4 equals 0.6288. Using the T83, 83 plus 84, 84 plus calculator Poisson, 4 equals 0. 6288 let y equals the number of calls that occur during an 8-minute period. Since there is an average of 4 calls per minute, there is an average of 8. 4 equals 32 calls during each 8-minute period. Hence y Poisson 32. Therefore, p y 40 equals 1, p y less or equal to 40 equals 1 0 92 94 equals 0. 707. Using the T83, 83 plus 84, 84 plus calculator 1 Poisson, 32 40 equals 0. 707. Try it 5. 13 in a small city. The number of automobile accidents occur with a Poisson distribution at an average of 3 per week. Calculate the probability that there are at most 2 accidents occur in any given week. What is the probability that there is at least 2 weeks between any 2 accidents? Stats Lab. Continuous distribution. Class time, names, student learning outcomes. The student will compare and contrast empirical data from a random number generator with the uniform distribution. Collect the data. Use a random number generator to generate 50 values between 0 and 1 inclusive. List them in Table 5.3. Round the numbers to 4 decimal places or set the calculator mode to 4 places. Complete the table, Table 5.3. Calculate the following. Letter 1D465 equals. S equals. First quartile equals. Third quartile equals. Median equals. Organize the data. Construct a histogram of the empirical data. Make 8 bars. Blank graph with relative frequency on the vertical axis and X on the horizontal axis. Figure 5.33. Construct a histogram of the empirical data. Make 5 bars. Blank graph with relative frequency on the vertical axis and X on the horizontal axis. Figure 5.34. Describe the data. In 2 to 3 complete sentences, describe the shape of each graph. Keep it simple. Does the graph go straight across? Does it have a V shape? Does it have a hump in the middle or at either end? And so on. One way to help you determine a shape is to draw a smooth curve roughly through the top of the bars. Describe how changing the number of bars might change the shape. Theoretical distribution. In words x equals. The theoretical distribution of x is xu 0, 1. In theory, based upon the distribution xu 0, 1, complete the following. Mu equals. Sigma equals. First quartile equals. Third quartile equals. Median equals. Are the empirical values the data? In the section titled, collect the data close to the corresponding theoretical values. Why or why not? Plot the data. Construct a box plot of the data. Be sure to use a ruler to scale accurately and draw straight edges. Do you notice any potential outliers? If so, which values are they? Either way, justify your answer numerically. Recall that any data that are less than Q1, 1, 5 Iker or more than Q3 plus 1, 5 Iker are potential outliers. IQR means interquartile range. Compare the data. For each of the following parts, use a complete sentence to comment on how the value obtained from the data compares to the theoretical value you expected from the distribution in the section titled Theoretical Distribution. Minimum value. First quartile. Median. Third quartile. Maximum value. Width of IQR. Overall shape. Based on your comments in the section titled Collect the Data, how does the box plot fit or not fit what you would expect of the distribution in the section titled Theoretical Distribution? Discussion question. Suppose that the number of values generated was 500, not 50. How would that affect what you would expect the empirical data to be and the shape of its graph to look like?